Learning objectives. In this chapter, the user would learn the following aspects of real-time operating system. Basic features of OS, task and task states, semaphores, RTOS architecture, RTOS task enrollment, RTOS scheduling, RTOS kernel, process and threads, synchronization and inter-process communication, comparison and study of RTOS, criteria for choosing RTOS. Basic features of OS. An RTOS performs these tasks but is also specially designed to run applications with very precise timing and a high degree of reliability. Main difference to other computation: time. Time means that correctness of system depends not only on logical results but also on the time the results are produced. Real indicates reaction to external events must occur during their evolution. System time or internal time has to be measured with same time scale as controlled environment, external time. To be considered real time, an operating system must have a known maximum time for each of the critical operations that it performs, or at least be able to guarantee that maximum most of the time. Some of these operations include OS calls and interrupt handling. Operating systems that can absolutely guarantee a maximum time for these operations are commonly referred to as hard real time. Operating systems that can only guarantee a maximum most of the time are referred to as soft real time. If missing its deadline makes the result useless, but missing does not cause serious damage, it is firm real time. Real-time systems are everywhere. Plant control, control of production processes or industrial automation, railway switching system, automotive applications, flight control systems, environmental acquisition and monitoring, telecommunication systems, robotics, military systems, space missions, household appliances, virtual or augmented reality. Task and task states. A task, a simple subroutine. ES application makes calls to the RTOS functions to start tasks, passing to the OS, start address, stack pointers, etc. of the tasks. Each task has its own context, not shared private registers, stack, etc. In addition, several tasks share common data via global data declaration, use of extern in one task to point to another task that declares the shared data. Shared data cause the shared data problem without solutions or use of reentrancy characterization of functions. Different states: running, ready, possibly suspended, pended, blocked, possibly waiting, dormant, delayed, exit, scheduler, schedules or shuffles tasks between running and ready states. Blocking is self-blocking by tasks and move to running state via other tasks interrupt signaling when block factor is removed or satisfied. When a task is unblocked with a higher priority over the running task, the scheduler switches context immediately for all preemptive RTOSs. Example: issue, scheduler or task signal exchange for block-unblock of tasks via function calls. Issue, all tasks are blocked and scheduler idles forever, which is not desirable. Issue, two or more tasks with same priority levels in ready state, time slice, FIFO. Scheduler switches from processor hog V levels task to V button task on user interruption by pressing a push button, controlled by main brackets, which initializes the RTOS, sets priority levels, and starts the RTOS. Semaphores. A semaphore, sometimes called a semaphore token, is a kernel object that one or more threads of execution can acquire or release for the purposes of synchronization or mutual exclusion. Multiple concurrent threads or tasks of execution within an application must be able to synchronize their execution and coordinate mutually exclusive access to shared resources. This can be accomplished using RTOS kernels, semaphore object, and associated semaphore management services. When a semaphore is first created, the kernel assigns to it an associated semaphore control block or SCB, a unique ID, a value, binary or a count, and a task waiting list. Counting semaphore. A counter is maintained for token counting. When a task acquires the semaphore, the token count is decremented. As a task releases the semaphore, the count is incremented. If the token count reaches 0, then no more resources are available and the requesting task is blocked. The task waiting list tracks all the blocked tasks of the semaphore. The list is implemented either in FIFO order or highest priority first order. When a semaphore or resource becomes available, the kernel allows the first task in the task waiting list to acquire it. If the task has the highest priority, the task moves to the running state. Otherwise, it moves to the ready state and waits for its turn. Note that the exact implementation of a task waiting list can vary from one kernel to another. A binary semaphore can have a value of either 0 or 1. If the value is 0, then the semaphore is unavailable or empty. If the value is 1, then the semaphore is available or full. A counting semaphore uses a count to allow it to be acquired or released multiple times. 0, the counting semaphore is created in the unavailable state. Greater than 0, the semaphore is created in the available state and the number of tokens it has equals its count. A mutual exclusion mutex semaphore is a special binary semaphore that supports ownership, recursive access, task deletion safety, and one or more protocols for avoiding problems inherent to mutual exclusion. The states of a mutex are 0 unlocked or 1 locked. A mutex is initially created in the unlocked state in which it can be acquired by a task. After being acquired, the mutex moves to the locked state. Mutex ownership. Ownership of a mutex is gained when a task first locks the mutex by acquiring it. Conversely, a task loses ownership of the mutex when it unlocks it by releasing it. RTOS architecture. For simpler applications, RTOS is usually a kernel, but as complexity increases, various modules like networking protocol stacks, debugging facilities, device input-output are included in addition to the kernel. Kernel. RTOS kernel acts as an abstraction layer between the hardware and the applications. There are three broad categories of kernels. Monolithic kernel. A monolithic kernel is one single program that contains all of the code necessary to perform every kernel-related task. It runs all basic system services, that is, process and memory management, interrupt handling, and input-output communication, file system, etc., and provides powerful abstractions of the underlying hardware. Amount of context switches and messaging involved are greatly reduced, which makes it run faster than microkernel. Microkernel. It normally provides only the minimal services such as managing memory protection, inter-process communication, and the process management. The other functions such as running the hardware processors are not handled directly by microkernels. Thus, microkernels provide a smaller set of simple hardware abstractions. It is more stable than monolithic as the kernel is unaffected even if the servers failed. That is, file system. Microkernels are part of the operating systems like AIX, BEOS, Mac, Mac OS X, Minix, and QNX, etc. Hybrid kernel. Hybrid kernels are similar to microkernels except that they include additional code in kernel space so that such code can run more swiftly than it would were it in the user space. These are part of the operating system such as Microsoft Windows NT, 2000 and XP, Dragonfly BSD, etc. Exokernel. It runs only services protecting the resources, that is tracking the ownership, guarding the usage, revoking access to resources, etc. by providing low-level interface for library operating systems and leaving the management to the application. RTOS services. 6 types of common services are task management, device input-output management, interrupt and event handling, timer management, memory management, synchronization and communication. RTOS task enrollment. In RTOS, the application is decomposed into small, schedulable and sequential program units known as task, which is the basic unit of execution. This is governed by 3 time-critical properties: release time, deadline, and execution time. Release time refers to the point in time from which the task can be executed. Deadline is the point in time by which the task must complete. Execution time denotes the time the task takes to execute. Each task may exist in following states: dormant, task doesn't require computer time; ready, task is ready to go into active state, waiting processor time; active, task is running; suspended, task put on hold temporarily; pending, task waiting for resource. A task object is defined by the following set of components. Task control block. Task uses TCBs to remember its content. TCBs are data structures residing in RAM, accessible only by RTOS. Task stack. These reside in RAM, accessible by stack pointer. Task routine. Program code residing in ROM. RTOS scheduling. The scheduler keeps record of the state of each task and selects from among them those that are ready to execute and allocates the CPU to one of them. Various scheduling algorithms are used in RTOS. Schedules or shuffles tasks between running and ready states. The data structure of the ready list in the scheduler is designed so as to minimize the worst case length of time spent in the scheduler's critical section. The critical response time, sometimes called the flyback time, is the time it takes to queue a new ready task and restore the state of the highest priority task. In a well-designed RTOS, readying a new task will take 3 to 20 instructions per ready queue entry, and restoration of the highest priority ready task will take 5 to 30 instructions. Various scheduling schemes available are: polled loop, sequentially determines if specific task requires time; polled system with interrupts. In addition to polling, it takes care of critical tasks. Round robin, sequences from task to task, each task getting a slice of time. Hybrid system, sensitive to sensitive interrupts with round robin system working in background. Interrupt driven, system continuously wait for the interrupts. Non-preemptive scheduling or cooperative multitasking. Highest priority task executes for some time, then relinquishes control, re-enters ready state. Preemptive scheduling, priority multitasking. Current task is immediately suspended. Control is given to the task of the highest priority at all time. Cooperative round-robin scheduling. Cooperative round-robin is one of the algorithms employed by process and network schedulers in computing. As the term is generally used, time slices are assigned to each process in equal portions and in circular order, handling all processes without priority, also known as cyclic executive. Cooperative round-robin scheduling is simple, easy to implement, and starvation-free. Round-robin scheduling can also be applied to other scheduling problems such as data packet scheduling in computer networks. It is an operating system concept. For example, if the time slot is 100 milliseconds and job 1 takes a total time of 250 milliseconds to complete, the round-robin scheduler will suspend the job after 100 milliseconds and give other jobs their time on the CPU. Once the other jobs have had their equal share, that is 100 milliseconds each, job 1 will get another allocation of CPU time and the cycle will repeat. This process continues until the job finishes and needs no more time on the CPU. Job 1 is equal to total time to complete 250 milliseconds, quantum 100 milliseconds. First allocation is equal to 100 milliseconds. Second allocation is equal to 100 milliseconds. Third allocation is equal to 100 milliseconds, but job 1 self-terminates after 50 milliseconds. Total CPU time of job 1 is equal to 250 milliseconds. Another approach is to divide all processes into an equal number of timing quanta such that the quantum size is proportional to the size of the process. Hence, all processes end at the same time. A round-robin rotation can happen because of the following events. The currently executed thread voluntarily goes into a sleep state. When the thread is awakened, it goes behind any other ready thread at the same priority level. The currently executed thread is preempted by a higher priority thread. The thread is reinserted in the ready list behind any other thread at the same priority level. If a thread with equal priority is ready, then the currently executing thread is preempted and reinserted in the ready list behind any other thread at the same priority level. Cyclic scheduling with time slice. Cyclic scheduling. Offline scheduling strategy. Divide the timeline into time slices for scheduling tasks. Example, use the greatest common divisor of the task periods as the time slice. Advantages: simple implementation, low runtime overhead, allows jitter control. Disadvantages: it is not robust during overloads, it is difficult to expand the schedule, it is not easy to handle non-periodic activities. Cyclic scheduling is sensitive to changes in the task parameters. Rate monotonic scheduling. Rate monotonic scheduling, RMS, is a scheduling algorithm used in real-time operating systems with a static priority scheduling class. The static priorities are assigned on the basis of the cycle duration of the job. The shorter the cycle duration is, the higher is the job's priority. A simple version of rate monotonic analysis assumes that threads have the following properties. No resource sharing. Processes do not share resources. Example, a hardware resource, a queue, or any kind of semaphore blocking or non-blocking busy waits. Deterministic deadlines are exactly equal to periods. Static priorities. The task with the highest static priority that is runnable immediately preempts all other tasks. Static priorities are assigned according to the rate monotonic conventions. Tasks with shorter periods or deadlines are given higher priorities. Context switch times and other thread operations are free and have no impact on the model. The basic priority inheritance protocol promotes the priority of the task that holds the resource to the priority of the task that requests that resource at the time the request is made. Upon release of the resource, the original priority level before the promotion is restored. This method does not prevent deadlocks and suffers from chained blocking. If a high priority task accesses multiple shared resources in sequence, it may have to wait, block, on a lower priority task for each of the resources. The highest locker protocol raises the priority of the task during its use of a resource to the highest among the priorities of all tasks that ever use that resource. The priority ceiling for each resource can be pre-computed at system design time. This protocol prevents deadlocks and bounds the blocking time to at most the length of one lower priority critical section. Preemptive scheduling. The preemptive scheduling feature allows a pending high priority job to preempt a running job of lower priority. The lower priority job is suspended and is resumed as soon as possible. Preemptive scheduling should be used if you have long-running, low-priority jobs causing high-priority jobs to wait an unacceptably long time. Preemptive scheduling takes effect when two jobs compete for the same job slots. If a high-priority job is pending, LSF can suspend a low-priority job that is running and then start the high-priority job instead. For this to happen, the high-priority job must be pending in a preemptive queue, a queue that can preempt other queues, or the low priority job must belong to a preemptable queue, a queue that can be preempted by other queues. Preemptive queue. Jobs in a preemptive queue can preempt jobs in any queue of lower priority, even if the lower priority queues are not specified as preemptable. Preemptable queue. Jobs in a preemptable queue can be preempted by jobs from any queue of a higher priority, even if the higher priority queues are not specified as preemptive. There are three ways to establish which queues should be preempted. Based on queue priority, the preemption parameter defines a queue as preemptive or preemptable, and preemption is based on queue priority, where jobs from higher priority queues can preempt jobs from lower priority queues. Based on a preferred order, the preemption parameter defines queues that can preempt other queues in a preferred order. Example, consider the case where three queues are defined as follows. Queue A has the highest relative priority with a value of 99. Queue B is both preemptive and preemptable and has a relative priority of 10. Queue C has the lowest relative priority with the default value of 1. The queues can preempt as follows. A can preempt B because B is preemptable and B has a lower priority than A. B can preempt C because B is preemptive and C has a lower priority than B. A cannot preempt C, even though A has a higher priority than C because A is not preemptive, nor is C preemptable. The number of job slots in use determines whether preemptive jobs can start. The method in which the number of job slots in use is calculated can be configured to ensure that a preemptive job can start. Critical section service scheduling. Critical section is a section in a system call OS function where there is no preemption by tasks. A disable interrupts function can be used at the beginning of a critical section and enable interrupts function executed at exit from the critical section to prevent preemption by tasks as well as ISRs. RTOS COS2 provides a function OS_enter_critical parenthesis to stop preemption by any task or ISR as it disables interrupts. The RTOS provides a function OS_exit_critical parenthesis to facilitate preemption by high priority task or ISR as it enables interrupts. Static real-time scheduling. A scheduling in which all the task characteristics, deadlines, periods, computation times, and so on are statically known. That is, they are known before the start of the real-time application. Scheduling decisions are made during compile time. This assumes that the parameters of all the tasks is known a priori and builds a schedule based on this. Once a schedule is made, it cannot be modified online. Static scheduling is generally not recommended for dynamic systems. Applications like process control can benefit from this scheduling, where sensor data rates of all tasks are known beforehand. There are no explicit static scheduling techniques except that a schedule is made to meet the deadline of the given application under known system configuration. Most often, there is no notion of priority in static scheduling. Based on task arrival pattern, a timeline is built and embedded into the program, and no change in schedules are possible during execution. Hard real-time scheduling. Hard real-time scheduling can perform fast admission and scheduling decisions for incoming applications while providing hard real-time services. Moreover, these algorithms provide temporal isolation, which is the ability to dynamically start or stop applications without affecting other already running applications. A variety of hard real-time scheduling algorithms for periodic tasks can be applied to schedule applications with a certain guaranteed throughput. Hard real-time tasks may have an absolute priority, with the system failing if a deadline is missed. If the system is to continue to run no matter what, then both hard and soft real-time tasks may be assigned relative priorities as a guide to the scheduler. Most hard real-time systems also have soft real-time components that can execute at lower priority levels to absorb the processor time that is not utilized with RMS scheduling of hard real-time tasks. RTOS kernel. RTOS is usually a kernel, but as complexity increases, various modules like networking, protocol stacks, debugging facilities, device input-output are included in addition to the kernel. Many operating systems, including most Unix, allow user processes to be preempted, but not kernel-level processes such as system calls. This is to protect kernel data that is in the middle of being accessed. There are three broad categories of kernels. Monolithic kernel, in that it alone defines a high-level virtual interface over computer hardware. A set of primitives or system calls implement all operating system services such as process management, concurrency, and memory management. Device drivers can be added to the kernel as modules. Modular operating systems such as OS 9 and most modern monolithic operating systems such as OpenVMS, Linux, BSD, and Unix, variants such as Sun OS and AIX, in addition to Multics, can dynamically load and unload executable modules at runtime. Monolithic kernels run device drivers inside the kernel space. Hardware interrupts are directly handled by kernel processes. To add or change features provided by the hardware, all layers above the change layer in the monolithic kernel also have to be changed in the worst case. The concept of so-called modules are introduced to achieve more independence and separation from the kernel. One module represents parts of a driver and is loadable during runtime. That way, drivers which are not needed by the system are not loaded and memory is preserved. But kernel modules are still binary kernel dependent. This means modules working with monolithic kernel of generation A, for example Linux 2.4.0, are not granted to cooperate with its successor, for example Linux 2.4.2. Source compatibility is often but not always assured. If concepts change too much inside the monolithic kernel, modules do not just need a recompilation but a complete code adaptation. Microkernel. A microkernel, also known as mu kernel or Samuel kernel, is the near minimum amount of software that can provide the mechanisms needed to implement an operating system. These mechanisms include low-level address space management, thread management, and inter-process communication, IPC. If the hardware provides multiple rings or CPU modes, the microkernel is the only software executing at the most privileged level, generally referred to as supervisor or kernel mode. The other functions, such as running the hardware processes, are not handled directly by microkernels. Thus, microkernels provide a smaller set of simple hardware abstractions. It is more stable than monolithic as the kernel is unaffected even if the servers fail, that is, file system. Microkernels are part of the operating systems like AIX, BEOS, Mac, Mac OS X, Minix, and QNX, etc. Many microkernels provide timeouts on IPC calls which limit the blocking time. In practice, choosing sensible timeout values is difficult, and systems almost inevitably use infinite timeouts for clients and zero timeouts for servers. As a consequence, the trend is towards not providing arbitrary timeouts but only a flag which indicates that the IPC should fail immediately if the partner is not ready. This approach effectively provides a choice of two timeout values of 0 and infinity. Recent versions of L4 and Minix have gone down this path. Mu kernels delegate the memory management to user space, controlling just the basic access rights. One of the servers is responsible for managing page faults and reserving new memory. Every time a page fault occurs, the request has to take the way through the kernel to the pager. The pager must enter privileged mode to get access to memory and get back to user mode. Then it sends the result back to the triggering process, again through the kernel. The whole procedure to handle page faults or reserve new memory pages is tedious and time consuming. Another argument for a true mu kernel is its code size. It is easier to ensure the correctness of a small kernel than a big one. Polled loop. Polled loops are used for fast response to single devices. In a polled loop system, a single and a repetitive instruction is used to test a flag that indicates whether or not some event has occurred. If the event has not occurred, then the polling continues. Example: suppose a software system is needed to handle packets of data that arrive at a rate of no more than 1 per second. A flag named packet here is set by the network, which writes the data into the CPU's memory via direct memory access, DMA. The data are available when the packet here is equal to 1. A single and repetitive instruction tests a flag that indicates whether or not an event has occurred. No inter-task communication or scheduling is needed. Only a single task exists. Excellent for handling high-speed data channels, especially when events occur at widely spaced intervals and processor is dedicated to handling the data channel. Synchronized poled loop. Poled loop response may be so fast that false events are induced by premature resetting of the flag. Switch bounce phenomenon in physical systems is a cause of such problems. Delay can be a no-op, loop, or interrupt clock driven delay. Increases response times, but it's worth it. Pros: simple to write and debug. Response time easy to determine. Cons: can fail due to burst of events, generally not sufficient to handle complex systems. Waste of CPU time, especially when event being polled occurs infrequently. Coroutines. Coroutines are very important as one of the very few examples of a form of concurrency that is useful and yet constrained enough to completely avoid the typical difficulties, race conditions, deadlock, etc. Synchronization is built into the paradigm. It therefore cannot, in general, replace more general unconstrained forms of concurrency, but for some things it appears to be the ideal solution. Simplest form of fairness scheduling. Processes voluntarily exit at strategic points of execution. Inter-process communication through global variables, sometimes called cooperative multitasking. Example, early versions of CICS. Coroutines will not preempt each other. Therefore, when a coroutine is selected to run, it will continue to be the selected coroutine until such a time that it blocks or calls yield. When a coroutine blocks the scheduler, then it reevaluates which coroutine should be selected to run and will at that time choose the highest priority coroutine that is able to run, that is not blocked. Coroutines use a cooperative system, whereas tasks can be configured to be either cooperative or preemptive. The priority is used to select the next coroutine to run at each decision point. It is the nature of cooperative scheduling. If you need preemption, then tasks are the only choice. Using cooperative scheduling, you have to ensure your low priority coroutines call yield often enough to ensure your high priority coroutines meet their real-time deadlines. Interrupt driven system. Interrupt service routine (ISR) takes action in response to the interrupt. Reentrant code can be used by multiple processes. Reentrant ISR can serve multiple interrupts. Access to critical resources in mutually exclusive mode is obtained by disabling interrupts. On context switching save or restore, general registers, PC PSW, coprocessor registers, memory page register, images of memory mapped input-output locations. The stack model is used mostly in embedded systems. Usually, an interrupt gives a signal from a device attached to a computer or from a program within the computer that causes the main program that operates the computer, the operating system, to stop and figure out what to do next. Almost all personal or larger computers today are interrupt driven. That is, they start down the list of computer instructions in one program, perhaps an application such as a word processor, and keep running the instructions until either A, they can't go any further, or B, an interrupt signal is sensed. After the interrupt signal is sensed, the computer either resumes running the program it was running or begins running another program. Multi-rate system. RM is a scheduling algorithm for periodic task sets. It is assumed that the periods of the different tasks differ. We have so-called multi-rate systems. Handling of single-rate systems is trivial. Jobs have priorities. Scheduler selects highest priority ready job. Two possibilities. Dynamic priority scheduling. Different jobs of task may be assigned different priorities. For example, job JI K of task TI has higher priority than job JJM of TJ. Job JIL of TI has lower priority than job JJN of TJ. Consider a task's characteristics: phase, period, execution time, relative deadline. Main goal: schedule job so that no job misses deadline. Fixed priority algorithms. Rate monotonic algorithm RM based on periods. Deadline monotonic algorithm DM based on relative deadlines. Rate monotonic scheduling. Priority definition. Tasks with smaller periods have higher priority. The rate of a task is the inverse of its period. Fixed priority algorithms. Priority definition. Tasks with smaller relative deadlines have higher priority. Earliest deadline first, EDF. At every scheduling point, job with earliest deadline is scheduled. DM is the same as rate monotonic if each task's relative deadline equals its period. DM is better than RM if the relative deadlines are arbitrary. When preemption is allowed and jobs do not contend for resources, the EDF algorithm can produce a feasible schedule of a set J of jobs with arbitrary release times and deadlines on a processor if and only if J has feasible schedules. This applies even if tasks are not periodic. If periodic, relative deadline could be less than, equal to, or greater than period. Precedence constraints are allowed. IPC and synchronization. An important and fundamental feature in modern operating systems is concurrent execution of processes or threads. This feature is essential for the realization of multi-programming, multiprocessing, distributed systems, and client-server model of computation. Concurrency encompasses many design issues including communication and synchronization among processes, sharing of and contention for resources. Independent process cannot affect or be affected by the execution of another process. Cooperating process can affect or be affected by the execution of another process. Advantages of process cooperation: information sharing, computation speedup, modularity, convenience. Producer-consumer problem. Paradigm for cooperating processes. Producer process produces information that is consumed by a consumer process. Unbounded buffer places no practical limit on the size of the buffer. Bounded buffer assumes that there is a fixed buffer size. Mechanism for processes to communicate and to synchronize their actions. Message system. Processes communicate with each other without resorting to shared variables. IPC facility provides two operations: send message, message size fixed or variable, receive message. If P and Q wish to communicate, they need to establish a communication link between them, exchange messages via send or receive, implementation of communication link, physical, for example, shared memory hardware bus, logical, for example, logical properties. Processes must name each other explicitly. Send P message, send a message to process P. Receive Q message, receive a message from process Q. Indirect communication. Messages are directed and received from mailboxes, also referred to as ports. Each mailbox has a unique ID and is created by the kernel on request. Processes can communicate only if they share a mailbox. Properties of communication link. Link established only if processes share a common mailbox. A link may be associated with many processes. Each pair of processes may share several communication links. Link may be unidirectional or bidirectional. Direct communication. Properties of communication link. Links are established automatically. A link is associated with exactly one pair of communicating processes. Between each pair, there exists exactly one link. The link may be unidirectional but is usually bidirectional. Message passing may be either blocking or non-blocking. Blocking is considered synchronous, non-blocking is considered asynchronous. Blocking. Blocking send. The sender blocks until the message is received by the other party. Blocking receive. The receiver blocks until a message is available. Non-blocking. Non-blocking send. The sender sends the message and continues executing. Non-blocking receive. The receiver gets either a valid message or a null message when nothing has been sent to the receiver. Benefits of multi-threading: responsiveness, easy resource sharing, economy, utilization of multiprocessor architectures. Suppose that we want to provide a solution to the producer-consumer problem. We have a limited size buffer, n items. The producer puts data into a buffer and the consumer takes data from the buffer. We can have an integer count that keeps track of the number of occupied buffer entries. Initially, the count is set to 0. It is incremented by the producer after it inserts a new item in the buffer and is decremented by the consumer after it consumes a buffer item. Synchronization hardware. Many systems provide hardware support for critical section code. Modern machines provide special atomic hardware instructions. Atomic is equal to non-interruptible. Test memory word and set value. Swap contents of two memory words. Uniprocessors could disable interrupts. Currently running code would execute without preemption. Dangerous to disable interrupts at application level. Disabling interrupts is usually unavailable in CPU user mode. Generally, too inefficient on multiprocessor systems. Operating systems using this are not broadly scalable. Shared data problem. Inconsistencies in data used by a task and updated by an ISR arise because ISR runs at just the wrong time. Data is often shared because it is undesirable to have ISRs do all the work. They would take too long to run. ISRs typically hand off some of the processing to task code. This implies shared variables or communication between the ISR and the related task. Normally not a good idea, but common in embedded systems. Compares two temperatures and raises alarm if they ever differ. The ISR updates the temperature variables. Assume interrupt asserted at regular intervals based on timer or when either temperature changes. Temperature rising, both values identical at each reading, say 80 at one reading, 81 at the next. Interrupt occurs between reading temperatures in task code. Test in main brackets compares old value with new value. Result: false alarm set off. Evacuations begin. General analysis required to detect and prevent. Suppose programmer decides that the problem is copying the data to local variables. Programmer changes the main brackets function but not the ISR. Code now tests array values directly rather than copying them to locals. In general, compilers cannot identify shared data. It is hard for humans to do, even when you create the code. No existing tools are clever enough to determine automatically when interrupts need to be disabled. Selective masking would reduce disruption to rest of system. Interrupts are disabled for a short period of time only. Increasing response time by 1 to 2 instructions is not a big deal. The overhead of disabling a particular interrupt generally higher. Details are platform dependent. Disabling all interrupts is a simple one-size-fits-all solution, but they better not be disabled for very long. Compilers are good at static analysis. Automatic detection would require a knowledge of possible dynamic changes. Use of semaphores. Synchronization tool that does not require busy waiting. Busy waiting wastes CPU time. Semaphore S system object. With each semaphore, there is an associated waiting queue. Each entry in waiting queue has two data items: value of type integer, pointer to next record in the list. Intuitively easy to use. Wait brackets and signal brackets are to be implemented as atomic operations. Difficulties: signal brackets and wait brackets may be exchanged inadvertently by the programmer. This may result in deadlock or violation of the mutual exclusion. Signal and wait may be left out. Related wait brackets and signal brackets may be scattered all over the code among the processes. Think about a semaphore as a class. Attributes: semaphore value, functions: init, wait, signal. Support provided by OS. Considered an OS resource, a limited number available. A limited number of instances, objects of semaphore classes allowed. Can easily implement mutual exclusion among any number of processes. Use of semaphores. In addition, there are two simple utility operations. Block bracket suspends the process that invokes it. Wake up brackets resumes the execution of a blocked process P. Define a semaphore as a class. Counting semaphore. Integer value can range over an unrestricted domain. Binary semaphore. Integer value can range only between 0 and 1. Can be simpler to implement. Example: nachos. Can implement a counting semaphore using a binary semaphore. Semaphore for synchronization. Execute B in PI only after A executed in PI. Use semaphore flag initialized to 0. Producer-consumer problem. Priority inversion problem. Priority inversion is a problematic scenario in scheduling in which a high priority task is indirectly preempted by a medium priority task, effectively inverting the relative priorities of the two tasks. This violates the priority model that high priority tasks can only be prevented from running by high priority tasks and briefly by low priority tasks, which will quickly complete their use of a resource shared by the high and low priority tasks. Priority inversion can also reduce the perceived performance of the system. Low priority tasks usually have a low priority because it is not important for them to finish promptly. For example, they might be a batch job or another non-interactive activity. Similarly, a high priority task has a high priority because it is more likely to be subject to strict time constraints. It may be providing data to an interactive user or acting subject to real-time response guarantees. Because priority inversion results in the execution of a low priority task, blocking the high priority task, it can lead to reduced system responsiveness or even the violation of response time guarantees. A similar problem called deadline interchange can occur within earliest deadline first scheduling (EDF) conditions. Concurrent tasks share a resource that is protected by, for example, a semaphore. At least one intermediate priority task exists. Solutions: avoid sharing resources between tasks of differing priorities. Turn off preemption of the low priority task for the critical section. The low priority task could raise its own priority while in the critical section. Priority inversion situation. At next instant T1, let task K become ready first on an interrupt. Now, assume that at next instant T2, task I becomes ready on an interrupt or getting the waiting message. At this instant, K is in the critical section. Therefore, task I cannot start at this instant due to K being in the critical region. Priority inversion problem. Priority inheritance. Some OSs provide for priority inheritance in these situations, and thus priority inheritance problem does not occur when using them. A mutex should be a mutually exclusive Boolean function by using which the critical section is protected from interruption in such a way that the problem of priority inversion does not arise. Mutex is automatically provided in certain RTOS so that the priority inversion problem does not arise. Mutex is automatically provided with priority inheritance by task on taking it in certain OSs. This does not happen because the given OS was such that it didn't provide for temporary priority inheritance in such situations. So that the priority inversion problem does not arise, and certain OSs provides for selecting priority inheritance as well as priority ceiling options. Criteria to choose RTOS. There are certain constraints considering while choosing RTOS: scheduling policy, runtime behavior, interrupt, API, event synchronization, memory management. Keep the following possible costs in mind: initial software license fee, recurring license fee, support costs, training costs, development labor costs, programmer, QA, manager, etc. Conclusion. In this chapter, the user has covered the following aspects of real-time operating system (RTOS). Basic features of OS, task and task states, semaphores, RTOS architecture, RTOS task enrollment, RTOS scheduling, RTOS kernel, process and threads, synchronization and inter-process communication, comparison and study of RTOS, criteria for choosing RTOS.